All right. Welcome. So today we're going to give an update on some of the tiered storage work we've been doing over in HDFS the last couple of years. I'm going to give a quick overview of some of the motivation and background for this work, specifically what's released in Apache 3.1, Apache Hadoop 3.1. And then Thomas is going to dive into more of the technical details on support for writes, and this work is ongoing. There are many people who contributed to this work. Thomas and I are just the ones talking about it. Particularly, we'd like to call out Viraj Jalaparthi and Ewan Higgs. Ewan is the newest committer on the Apache Hadoop project as of this morning, so congratulations, Ewan. Come on. There we go. Okay, so Hadoop ecosystem applications already work across a range of storage systems, including some object stores. Specifically, and by work with, we mean something pretty specific sometimes, which is the file system specification that's maintained in the Apache project. And then after that, they're kind of tested to correctness. Which is something we'll get to later in the talk. And so for most of the deployments using object stores, they're scaling compute and storage separately. That's one of the motivations for this. And while that gives you a lot of flexibility operationally, it isn't perfect because your file system abstraction, the code that translates whatever you're doing in your Hadoop application to the object store, is not really a file system. So some operations, even if semantically they match the contract, the performance guarantees are going to be unlike those that you get in HDFS. You can rename 1,000 things really quickly in HDFS. That takes longer in these systems, by way of example. A lot of the Hadoop applications are tuned as if they had local replicas. This is generally not the case in these environments. So it's not just the latency that can be increased. That's usually not a problem for throughput-driven applications, but the variance in latency and throughput, which can make meeting SLOs unduly complicated. Again, I cite the testing to correctness and over-provisioning and increasing costs when you move to these elastic environments. And finally, there's a whole ecosystem of things around HDFS specifically. These are plugins that affect how it implements security, and access control, specifically like Apache Ranger, Apache Sentry, a long list of proprietary technologies people have built to wire into clusters that they, company goes out of business, but you still need to support it because you have a line of business that depends on it. So our goal is to have not just Hadoop, but have HDFS play nicely with object stores and with these other applications in order to carry the whole stack with us. And we do that not by emulating what HDFS does and being specific about the specification. We do that by just running HDFS and building machinery to coordinate what's happening in the remote store. We do this by way of a storage type called provided, which is a peer to all of the other types of local media that you can attach to a data node. And we maintain not just the data dependencies, we also are able to mirror the namespace or provide a mapping between the two namespaces in ways that are operationally interesting. So ideally, this can mean that there are no change to your existing HDFS workflows. You can even introduce tiering into an existing on-prem cluster. Pretty organically, and with constraints we'll get into later in the talk. The tiering part happens asynchronously in the background because, again, the matching up those guarantees, there's nothing magic about it. We can't make that go away, but we can hide some of that latency by batching writes and prefetching on reads. And of course, because you're running literally HDFS, it has support for all of your existing, any of the plugins that you might be relying on. The rest of this I'm going to skip because we started a little late. So what we're talking about is doing a mount. Right, so we're mounting some remote storage inside of HDFS. We covered a lot of this in the talk from last year, but just to run through some of the terminology, we maintain for every block in the HDFS namespace an alias. An alias corresponds to a fixed range of bytes in the remote where that includes a nonce to detect whether or not those bytes have changed. So we never will serve different data than what we generated the image with. And the way that you coordinate between the two namespaces is by using the existing mechanisms inside of HDFS. So that means you can change replication in order to affect prefetching of a file, as we'll get into later. So if I have two different namespaces, I can create a mount point. This is again just like going through terminology we're going to keep coming back to. I can create a new mount point inside of HDFS that reflects, whatever I'm showing in the remote namespace. I could also come up with a different mapping if I didn't want to show, like as in this example, DEF as DEF. I could show them as something else. I could even do on-the-fly translation if I want to get really crazy about it. And we then maintain a mapping between each of those blocks and the alias in the remote store. That's the mechanism around which we build, all of our abstractions. So to run through a few examples, if pick your metaphor for persistence, but laser doesn't work. But if you're looking at like dehydration, if I have a set of objects that are in my remote store, and if one of them is a namespace, behold my PowerPoint skills, I can restore that namespace, and then for all of my reads, I can do a direct map between all of the blocks that I've persisted in the remote store, and I can just wire them, just send them through the data node. So I can start up HDFS, and without copying all of the data into HDFS, I can access whatever's in the remote store. But these have to be, it's a direct map, and if I tried to view those files on the remote, they would just appear as blocks. I have to start a name node in order to work with them. The case that gets a little more interesting is a lot of the infrastructure as a service layers where people are building Hadoop clusters on top of existing data that they might have in the cloud already. And here we provide a mapping between each of the blobs, which are represented as files in the remote store. And when I do a read, for say the second block, for data that exist in the second block in bar, then I can read off of that range of the blob in the file system. What this also means is that if I set replication for bar to be above the single logical replica that's stored remotely, then HDFS will, just as part of satisfying its replication policy, store local replicas of that block data inside of the whatever local media are attached to my data nodes. And all of the other machinery like quotas and things like that still apply. Again, building on this, you can combine this with federation, where I can create a separate name node that serves up, some of this remote data, and whatever, however it's stored on the in my remote store, I can just proxy that part of the namespace through, and I can share the storage with other existing name nodes in my federation. This works for Federation Classic and Federation with routers, whatever you're into. I don't judge. But sorry, I need to go back. The emphasis that I want to lay on this is that tiering is trying to mix with all of the existing HDFS features. It's not trying to place all of the dozens of ways that data are already coordinated between different storage systems and even HDFS on HDFS. It is trying to be a mechanism that is a good partner with all of the other existing abstractions in there. So let's be concrete about what's actually released. What you can do in 3.1 is generate an image from a remote store and start a data node, or excuse me, start a name node, start an HDFS cluster that will start serving those data immediately. And so this is code that we've spent a lot of time hardening. We spent a lot of time, working with the community to make sure that it's pretty solid. And we're running it at Microsoft right now. But it is limited. It's static. If you make changes on the remote file system, you will never receive wrong data through your image, but you won't receive updates either. And so, moreover, we will not receive, if you write data into that mount, it's not going to be persisted. But that work is what we're talking about in this presentation, right? Is how to persist the data back, which is not to say we've not played around with this abstraction a lot. Virajit and I are in a lab, so we do a lot of things that are not real, but they look really cool. Including some of these actually do work, like demand paging. Like if you wanted to do read-through replicas, if a new replica shows up, the name node will dutifully delete it, right? Because it shouldn't be there. It doesn't match the target replication. So we've been playing around with a concept like elastic replication, so that I can increase the number of replicas that I have stored in local media depending on how hot the data are and things like that. We've also done sort of a optimal prefetch schedule for recurring pipelines, so that by the time the job starts inside of your cluster running in the cloud, the data are already local. They're already in the local media, right? So you can actually have some reasonably tight SLOs around those jobs. The people who know HDFS well will ask, so what happens if this storage type shows up in my write pipeline? One of the ways that we worked with the community was making sure that the state machine, like the block state machine, the replica state machine inside the data node, can handle provided blocks. And so you can implement right through using this, plus or minus some edge cases, which for the purposes of this talk, I'm going to wave my hands and say it works okay. We've even done some really crazy stuff, like trying to run a separate name node per application and be able to get a snapshot of input data, wire it back in, and things like that. So we've been playing a lot with this abstraction. We're pretty confident that it's not just covering the cases we're talking about today, but it's actually generally useful inside of HDFS. But one of the things people ask is, so how do you keep, what you're talking about looks like a, multi-mastered. So I know that's really complicated, so we're putting most of that out of scope for this project for the near future. Couple more notes. Running these things in the cloud. Again, we did some measurements on the variance that you get for writing. This is on 100 trials, writing 512 megs to and from remote and local storage. And the takeaway from this is it's by this coefficient of variance, by a measure of unpredictable invariance, it's 5 to 30 times as unpredictable as using local storage. And so we wanted to find a way, a mechanism to be able to draw remote data into local data nodes so that the applications actually run on these local media. This is critical, especially if you're dealing with someone who has an on-prem cluster. They want to start running it in the cloud, and you have to give them a system of equations to describe how their reads and writes work. It's a very different environment. So the more we can make it look and behave like their local cluster, the easier that's going to be, and the less they will not have to rewrite most of their applications just because they're running them in a slightly different place. So another question we often get is, I have a favorite caching file system. Why don't you use that? And it's a very fair question. If you're looking at Luxio, Rubix, some of the even the stuff on my Twitter with nfly and modifying ViewFS, you can look at multiple clusters and read from the local one, things like that. So a lot of these are trying to add new capabilities. So they try to make they try to add a key value in an object store and make that consistent with their own file system implementation, or they want to add multiple file systems into some sort of unified union file system. And that's a very laudable, winsome goal, but it is still going to be limited in HDFS compatibility. It's not going to support the entire ecosystem of applications and plugins that we're trying to capture with this work, because the applications they're talking about, they're correct. They target this file system abstraction. The deployments all run HDFS. So the operators care about how your caching file system would manage audit logs, how it would handle rolling upgrades, how you would be able to decommission nodes. And even if it supports all of these operations, there are sites that already have predefined procedures for how they do this with HDFS. And we want to support that because it's useful for those people running HDFS. Anyway. Point belabored. We can move on. So the way that typical read works, you ask the name node for locations, you get the locations, you read them through. What we can do is we can create a mount on the object store, mount a provided storage type and provided storage attached to each of these data nodes. Internally, the NameNode associates a storage with one and only one data node. We violate that a bit and say that no, this provided storage is actually owned by a set of the data nodes in the cluster, which means that when you join, when a data node joins the NameNode, if it reports that provided storage, that means it can access any of the blocks that are accessed in that storage. So we can drop immediately out of safe mode. So we can persist the namespace and metadata going back. Let's say we lower our replication for all of these files to 1. So I now just have the one logical replica of these blocks in my HDFS cluster. Excuse me. But then when I ask for the location, I go to the provided replica. It maps the block ID to that same immutable set of bytes that I wrote back originally. And I can return that through the data node back to the client, maybe doing some caching. With that, I'll hand it over to Thomas, talk about how we do writes.
Yeah, so Chris just demonstrated like the data flow for how we would tear out stuff from HDFS to the object store. And I'll try to, in the rest of the talk, reiterate how we would do that, what properties we care about, and how some of the technical details work. So you could see this as Dropbox TM for Hadoop. So you have your laptop, you have certain files on there, but actually it has the entire namespace, but it might not have all the data. Some of the data would be in the cloud. So we want to have a similar system for Hadoop where your cluster has a complete namespace, but only the working set of the data. And cold data might be stored in the object store. And so when you try to get one of these cold data, as Chris demonstrated in the previous slide, the data node actually gets it for you in the object store and transparently offers it, proxies it through to the client. So you can page in missing data on read, and writes happen asynchronously. So Dropbox for Hadoop is something which you can call this, or your phone app works the same way for your photo app on the phone. If you have certain photos, the last photos are on your phone, and the other ones are in the cloud. If you scroll down enough and you click one, you see a spinner. It's actually getting it from the cloud and moving up. So we want to make a similar system for Hadoop, where the cold data or the more archival data gets tiered out. And so we do this, as Chris mentioned, we do this by using a storage policy. And so the storage policy and the replication count together give us rich placement options. So for instance, for hot data, you could have a storage policy which has storage types SSD provided, which means you have one in-cluster copy which is fast, and you have one in the provided store for durability. Depending on your needs, you could even have multiple SSD copies in cluster, or some SSD, some issue, and you get the idea. So, and then for the cold data, you can solely have only the provided type, and then use when you want to access it, the data nodes can transparently proxy it through. And so one of the things you get is by using a dedicated object storage system, you can do these things more efficiently. So in the Hadoop project, so also heterogeneous storage, when the storage types were introduced, I think 2.5 or 2.6, I think by eBay and Hortonworks, they also had an archive storage type, which basically had the same idea. We're going to have this fat data node. It runs no compute. It's just a storage-only data node. This is basically the same idea, but we say like, okay, external systems who are dedicated for doing this will use those instead. And so because they have features like multi-geo replication, so multi-data center replication, erasure coding, a bit more rich options there. But we want to do it in a certain way, and this is very, very important, that the file object mapping is preserved. So when we tear it out, we just don't want to tear out the block. We actually want to reconstruct the file as an object, or if the other backlink system is another HDFS cluster, it's going to be a file again. But you want to preserve the mapping. You want to synchronize the namespaces as well. And so this means that if you tear something out, for instance, to S3, you can use any S3 client to access that object. Same for Azure. You use the REST client, you use an SDK, it all just works. So I think last year we presented the read part, which Chris showed earlier in the first slides, and so we got some community feedback on that. So these are tweets from like 1 year ago, just after this presentation. Zay at LinkedIn really liked this idea about an SSD, fast locality-aware SSD cache in the Hadoop cluster and then a blob store outside. And Alan, who's the Hadoop ops guy and big lover of branch 2, he also really liked this idea of this way to do cold storage. So when just in the hallway just now, people like Western Digital, what are you guys doing with Hadoop? I mean, when we standing next to Chris, they know what Microsoft's doing with Hadoop. So actually, we're in the data center systems business. So we basically make an S3 compatible object store, and evidently that's where this comes in. We've been contributing to the S3A connector, where Steve Laughlin from Hortonworks is doing a lot of work. And I think for the last 2 years now, we've been working on this project of having a provided store to also integrate HDFS with object stores. And so that's where this ties in together. And so I think Ewan indeed has been one of the main drivers for that project on our side. We actually have a demo, if it's managed to copy from the USB drive by now. So the demo is basically going to demonstrate that we're going to configure a directory varlog in HDFS. We're going to set a storage policy to provide it, and then we're going to start the sync service to actually go from varlogs to a bucket in S3. So Hadoop logs, the bucket Hadoop logs. So you can see here that actually we still use the S3A file system, so it uses the existing object storage file systems which are there in Hadoop today. But this is abstracted away. It is the data node who uses this, and it's no longer the application who directly uses these file system connectors. This has a fancy thing. This was expected. Let's see if there's a better player here. There we go. So basically on the top you just see some logs. That's not super interesting. So the setup is we just have a VM of one of our system, an active kill system, and we have a Hadoop cluster probably on, I think it's on Ewan's desktop, where this demo went on. So we have an S3 compatible VM, and we have a local HDFS setup. And so we created a directory backup. We set the storage policy to provide it on the backup path. So we start the sync service. So it's called here fake Apache logs. So it's just a bunch of Apache logs which we're going to sync between backup and HDFS in the NameNode namespace to the backup bucket in S3. And then now, so you can see backup attached to backup with. So this thing is now attached, and now we're going to copy in a bunch of files into this backup directory on HDFS. So 853 log files to be precise. And so now this script is running, and it's actually writing files to HDFS. And at the same time, HDFS is in the background asynchronously replicating to the object store. So in the new screen, we just use an S3 client, S3CMD, to list this directory and then do a count. So you see the number of objects in the S3 increasing, 139, 130. So let's skip ahead a bit in the interest of time. I think close to the end, here you see that 850. So things are happily going on. So the writes to HDFS are still ongoing. So now this returns. So now HDFS is ready. You can see 842. We still have a couple of files to back up. And like I think in a couple of seconds, all of them should make it over there. So basically, this allows the admin, by setting the provided storage policy, configuring a sync service, it allows him to tear data out of the cluster. And then the admin can decide, by setting a certain storage policy, if he wants to keep the in-cluster replicas or he wants to rely on the provided only. So we're done here. I think next thing that's happened is that we actually start deleting stuff again. And you see that as you delete them from HDFS, also the deletes are propagated to the backing store. And eventually we end up with only one object in the industry anymore, which is just the directory, the fig directory object. So let's try to get back into the presentation. Okay. So we now cleared it out. We still have in-cluster replicas. If you would now change the storage policy to provided only, the in-cluster replicas would be garbage collected, and then you would rely solely on the provided store. So to reiterate some of the requirements, what we really want is preserving this file object mapping. I probably said it 3 times already, but it's really important. And I think Chris explained that this was HDFS 9806. It got merged, I think, in December. And so this is the alias map we talked about last year. And so the data nodes collaborate to actually move the blocks which constitute a file in HDFS to the object store to create an object which has the same data. And so we want to do this in an efficient way. We are not choosing a data node, reconstructing the entire file over there, and then sending it out to the object store. No, we are using actually constructs which allow us to do that parallel directly from the data node, go into the backing store. And if the backing store is S3, you can do that with the multi-part upload. If it's Azure, you have append blobs. And if the backing store is HDFS, we create a temporary directory. For every block, we write a file there, and in the end, we concat them together into the final destination. So actually, also on HDFS, by using a temp directory, you can use the same parallel construct. And this allows you to just copy multiple blocks in parallel, constituting a single file. So deployment-wise, this is a new service which could run inside the NameNode, it could run outside. If it's inside, it's easier to deploy. You don't have to worry about HA, but evidently it will use some resources. So there's an ongoing discussion within the community to figure out if we want to offer both these options or only one of them, but definitely we're going to need the external one. So we're starting with the external one, and then we can see where that discussion with the community goes to. We wanted to do like one technical deep dive, a little bit more detail about how we actually do the synchronization, how we determine which work needs to actually be moved out. So we have a mount manager which manages the local mount points. And we use the snapshot mechanism in HDFS to take snapshots of these mount points periodically, and then we use the diffs between these snapshots to figure out what has changed. Again, so this is this new service which would do that, the sync service, which can run in or out of the NameNode. And so based on that diff, we need to generate a phased plan. So there are multiple ordered phases in the plan, and then because for instance we first do the renames, then we do the deletes, then we do the creation and of directories, and then creation of files. So for instance, if you need to create a directory and then a file, you cannot do that the other way around. You cannot do those in parallel. You need to first create a directory and then the file in that directory in the other store, in the external store. So we need to have a certain ordering. But we group these things in multiple phases. Within a phase, we can do all the operations in parallel. For instance, creating 100 files, you can just open 100 parallel uploads to the backing store. And then that's already executing the work. So once we have this plan, we can execute this plan, do all the parallel uploads. So those are mainly served by the data nodes doing the data operations, and then the sync service does the metadata operations. And the admin can track the progress through the CLI. There's a CLI command to track like this mount point we're working on, the diff between these snapshots, and this is our progress which we're making there. So we went for snapshot diffs and not for like post-processing the edit log, which would have been another possible way to do this. What we really like is that a snapshot reflects a point in time 100% accurate state of HDFS, and then we're going to try to realize this state in the backing store. And so the nice point of Snapshot is that it not only retains the metadata, it also holds on to the blocks of data which existed at the point in time the snapshot was taken. So if a block ID is referenced in the snapshot, it's available, you can actually go and get that data. So I tried to make a diagram. So my colleagues here made fun of me. For me, time moves from right to left. Maybe that's because I'm from Europe. So we have a snapshot 5 here and a snapshot 6 which is taken. There are snapshots before and there will be snapshots in the future. But so if you look at a file A, so green means we create a file and red means we remove it, we delete it. So if you look at file A, it's created between snapshots 4 and 5. So at the point as we take snapshot 5, we can detect by comparing 4 and 5 that A has been created. And then a bit later, A is deleted, and then by comparing snapshots 6 and 5, you can figure out that A is gone. So those are the kind of things we can pick up. Something like object B, which is quickly created and then immediately deleted. Yeah, you can see the time of snapshot between 5 and 6, it's not there twice. So we can't pick those up. We're really interested in, for us, the real point is at the time of snapshotting, there is a certain point in time view on the HDFS file system which we can completely realize. So that's what we really wanted to do. And so if you do this based on the edit log, so you just get, it's like a, let's think about such an edit log, Kafka log with all the changes in the system. You could just read that. To parallelize that, you could also take batches of those, like I'm going to read the next 1,000 operations and then execute them in parallel. Of course, you get the same problem that you have with the snapshots, that you need to order certain operations, so you would need to do something similar with phases. But the main thing here is that this does not hold on to the data. So in the meanwhile, this is just post-processing of the edit log, and the meanwhile reality might have changed. So files can get deleted actually before you can post-process their creation. And there's no way to hang on to data in this mechanism. So if we would want to have the same guarantee that if we take point in time in this edit log, we want to completely realize this state, we would have to have a mechanism to postpone garbage collection in the NameNode. And we really liked the fact that Snapshot already offers you a high-level abstraction to achieve that goal. And yeah, we didn't really like that, to break the separation of concerns, that removing block IDs would now be in this sync service outside. That seemed like very, very scary. So the snapshot thing actually gave us what we wanted. Quick example. So this is a simple example, then there's a little bit more complicated one. So what happens, so given a certain directory basic test, we are going to create a directory ABC, and then we're going to make a file abcd f1.bin, and then just a file in basic test f1.bin. So what happens if you look at the snapshot diff report, that will just tell you like, hey, there's new stuff in A, and I created a file f1.bin. And so based on that, we just know there's new stuff in A. We need to crawl, iterate in the snapshot to figure out what changed, and then we can create this phased plan where here, first we create a directory abcd, then we go to the next phase where we start creating files. So in abcd, we create f1.bin, and in the top level directory, we can also create f1.bin. So this seems kind of straightforward, but things can get more complicated. So here we're swapping a file. So we're moving from a.bin to temp, from b.bin to a.bin, and then from temp to b.bin, a classic computer science swap using a temp file. And so basically the snapshot diff report just tells you A becomes B and B becomes A, which of course is not really an executable plan on most external storages. So here we then have code to then reintroduce a temporary location to do the moves in a secure manner. So seems like even with the delayed start, we seem to make it more or less within time. For a couple of, we have 3 more minutes for questions. So HDFS 12090 is where this write work is going on. And there's loads of people in the community who have been helping out, giving feedback. So if there are any questions, ask them now or come find us. We're around for a while, next couple of days. Thanks.
there's a. Okay. Do you want to ask your question at the mic?
Any questions? There's a mic up front. But okay.
What about Ranger integration for the blocks actually?
Ranger integration.
Oh, so the Ranger integration is just going to be at the namespace level. So if you tie in Ranger into the NameNode and that defines some policy for how you're going to be accessing files, then that's applied at the NameNode. You don't need to, by way of example, if I had a set of Ranger policies and I wanted to run those on an external store, I would need either some arbitrating proxy to do that, or I need to figure out how to translate those rules into whatever the external store offers to implement comparable policies. And so by just running it in HDFS, HDFS is still responsible for enforcing them.
And the second question is that, what about the storage policies defined by third-party storage, like Pure Storage or NetApp or EMC storage? Do you have?
So you mean like the FlashBlade stuff, like
No,
the
it can
object
be
store?
Flash or maybe fiber channel or InfiniBand, different
Right.
tier storage, right? So
Right.
do you able to integrate their storage policies with this one?
So what you'd need is a file system shim, like an implementation of those APIs, and then we would use a subset of those in order to implement the tiering, right?
Okay.
And so as long as that exists, you're fine. You could also implement the more simpler API on top of that. That's just putting and getting blocks.
So
right?
I think we integrate with S3, Azure, other HDFS. So you can make basically, if you can have a file system that will have the same abstractions there, you can make whatever you do. You want.
So we do need an adapter, but it's simpler than a file system implementation.
Okay. Thank you.
Thank you.
Anyone else? It's lunchtime, so we have some time.
Yeah. So how does the integration between HDFS and the object store support Kerberos?
So you'd have to run your own KDC for the Hadoop cluster. And you would also need to define a mapping between the users, or the whatever ownership you want is in the remote store, into the FS image. So you create an image that has a set of users, and that's there's a plugin in the file system generator where you can define what that mapping looks like, right? But all of the users that the KDC knows about, or Active Directory or whatever you're using, that would be authenticated through HDFS. Would have to be present in the image, and then HDFS enforces that on the back end. So by way of example, if I have credentials for accessing the back end, those would not be accessible to the users who are accessing it through Hadoop. They would still be they would be in a secure Hadoop environment. On the back end, you could use, one use case we have is we have people who have like a single container with a single set of credentials where the permissions on them are polite suggestions that users please not access each other's data. And so what we've tried to do is have HDFS enforce that, tuck the secret behind the data node where users can't get it. And this abstraction works well there. Did I answer your question or not quite?
Kind of.
Kind of. Okay.
I think I need
Do you want to try again?
digest
Or?
it.
Yeah.
No.
Okay. Let's talk after.
All
Let's talk after.
Anyone else or people hungry?
All right. Yeah.
So-
Thanks for. Go ahead.
I've got one more. When you're applying policies, whether it be, to SSD or to the provided, are there ways to do that that take into account how often a file is used, or how do are you manually applying those policies now, and can they be based on file metadata?
So there are a few related projects in this space. So there's smart storage management, which was a issue proposed by Intel, which was looking at these kinds of policies. So if I have access logs and I want to merge those with let's say a schedule for jobs that are about to run, then I could come up with a script that runs in this external server that sets all of the policies and then tells the NameNode to start moving stuff around to satisfy them. So one of the original goals of this was to be compatible with that. Some of the work that Viderjit and I were doing was a little more both short-term and long-term, right? So there's the like demand paging, where it just does read-through caching. So whatever ends up in your local media will be whatever was kind of read recently. We're also looking at prefetch schedules. So if you know when jobs are going to run, you just set the replication early enough. You set the rate at which they're going to be fetched, and you can you can manage the working set for your HDFS cluster. And so particularly if you're in the cloud setting, that means you don't have to over-provision as much. You don't have to spend compute resources on copy jobs, stuff like that. Just operations a little easier.
Thanks.
Sure.
Okay, thank
All
you.
right. Yeah,
If there are more
thanks, everyone.
questions, come and find us.
Yeah.
Thanks.